Okay, so in the last video, we set up a KD tree, and then we set it up to turn blocks visible within a 10 unit radius and invisible within a 15 unit radius. So this system's important for scooping up objects that are in the far range and getting rid of them without over-iterating and trying to turn too many objects invisible or too many objects remove their physics object that don't have one. So you'll notice this doesn't really use that much resources, and it's iterating through not a lot of objects, but I don't think that adding a bunch more of these is going to do much. Unlike in Python. Yeah, it, it didn't even add 0.1 seconds to logic, adding all those objects. Let's make sure. So this is really what KD trees are good for, is looping through a bunch of data and making sure. Okay, so that raised it up a little bit, but probably a lot less than Python would. We could just test it out and see. House is making creepy noises. I don't really know what that was, but okay. So let's comment these out. And try and do the same thing with Python and see what happens. I think the only real fast way to do this in Python would be to build a list. Alright. New dot append. Okay. So we're going to build a list of lists. And I'm going to crack open Rectified here real quick and grab something out of it. I'm sick of looking this up. You know, I might not even have it in Rectified. This one that's in the older one. Yeah. Oh, I do. I do. In my laser script. So this is a really useful chunk of code right here. This is for sorting a list based on the second value of the list. So we type new equals new. So it's saying sort, and then the way that it sorts it is with this key lambda, and then it says that it's going to use the tuple, and it's going to use the tuple part 1. Okay, so that'll sort them all by distance. So you can get the closest 10 objects by grabbing the closest 10. So that's equivalent to a KD tree, kind of. All right. Let's just see how long that takes. It's already looks a little bit slower, just to do that one operation without operating on any of the objects. Let's see here. Get near and far and turn the objects visible and invisible. Let's see how much that costs. Oh. Looks like we're throwing an arrow. What we got going on here? Oh, we're printing a bunch of stuff. So yeah, it looks like it uses more resources just to sort the list the first time, let alone to operate on anything. So the KD tree is definitely faster. Here, let's see exactly. We'll get rid of the invisible and visible. So yeah, this uses 0.17 when not operating on anything, and just appending and building the near and far list. And this uses 0.32 just to build the sorted list. The closest 10 would be the first 10 objects and all that. So this is handy, don't get me wrong, but this is superior. Alright, so next, we'll leave all of the objects, we'll turn all the objects visible, and instead of replacing their, turning them invisible and invisible and visible, we will add their physics objects and remove them, which is a common scenario that you'll need. Is there's objects that you'll be able to see sometimes and not need to interact with unless you're close enough. So Xbox controller turned off, and turn my mic off for a second. So copy. So now these should all be visible. Alright. But we're going to do a step further and do no collision. And this static tag, we're going to change it to a string. Alright. So we grab the properties and the physics out of the one copy so we don't have to do it to a million objects. So now we'll turn physics on, and you'll notice none of them have physics. Okay. Alright. So we'll look up each item using the index. So rather than adding an object every frame and having it dissolve, or adding a bunch of extra objects or having problems like that, We'll make sure that we only add it once. With this. Clean this up a little bit. All right. So we're going to store the physics object that we create as the property phys. And then if the property's in the game object, in the far list, we will delete that property and delete the physics object. All right, so this should work. Oh, we have to. All right. There we go. Physics LOD. Oh, looks like we tripped out an error. Okay. So it's saying that the data has been freed, even though we're deleting the object and deleting the data and all that stuff. So the best way to fix this is if target.invalid equals false. All right, we shouldn't trip on that error now. Nope, there it goes. $35. Oh, up here. That's weird. Duh. Target dot end object. Duh. There we go. I was being silly. Now we'll set up a practical scenario. All right. I'm going to put all these on their own layer. That way, to select them, it won't be such a pain. So, watch the physics usage. So it'll never get higher than that. That's the max physics usage. Right now. Then we'll take all these and turn them static. Okay. And then take our cube and turn it no collision so it doesn't interfere with the physics data. Oops. All right, now. So we got about 25 milliseconds on there. 5 right here. But of course, these are really super simple physics bounds. And I'd imagine that it'll be more drastic the more objects there are. All right, in this scene, we're using about 0.9. In this one, we're still using the exact same, almost 0.3. So, there we go. Confused me there for a second. All right, so there we have Physics LOD and proof that it works. So in this scene, which isn't even a full scene, it's saving about 0.6 milliseconds of logic, and that is our physics. That is 432 objects, which is not that much. When the grand scheme of things, a large maze could have 10,000 objects. And that's the first case I found to use this, was Battery's maze. I made a large maze, and the physics were preventing me from using the maze. So I came up with this.